for this spring period of time. I am happy to introduce today's lecturer, who is Birol Ozturk. A short bio for Birol is the following. So Birol Ozturk is an associate professor in the Physics and Engineering Physics department at Morgan State University. Dr. Ozturk holds a PhD in photonics from Oklahoma State University. After working as a postdoctoral research associate at Brookhaven National Laboratory and Syracuse and Northeastern Universities, he joined MSU in 2014 as an assistant professor. Birol's current research interests include quantum sensing with defects in wide bandgap semiconductors. Birol, the stage is yours.
Thank you. Thank you for the introduction, and thank you for the opportunity for this talk. So, as mentioned in the abstract, I'll be talking about our recent progress with using NV-diamond for quantum sensing applications. So I'll be talking about how we use nanodiamond for different applications, and also our recent results on developing compact quantum sensors based on NV-diamond. So, as mentioned in the introduction, we do research with wide bandgap semiconductors, defects in wide bandgap semiconductors, mainly for quantum sensing applications. So using solid-state defects essentially, and they are very abundant. As you can see in this nice graphic from this publication, there are many active defects in optical active defects in different wide bandgap semiconductors, and they are being used for quantum sensing applications, and the NV-diamond being the most prominent. Perhaps the HBN and silicon carbide defects are also following. And in my group, we do work with actually on different defects, different materials. I'll be talking about NV-diamond today, but we also look at defects in 4H and 3C silicon carbide. So 3C here, 4H looks like I forgot to mark it, or yeah, the V1, V2 defects here. We also look at their properties, and also 2D materials. There's tungsten disulfide here. I also forgot to mark it, but we also look at defects, and actually in this case, mainly focused right now on the exotonic behavior and how they relate to defects. We are trying to understand it, but also trying to see if we can use these defects in these 2D materials as well for quantum sensing applications. It has not been demonstrated except HBN, as you may know, for this field. And another interesting material is the cubic boron nitride. We are after this ONVB defect. We haven't observed it, but we did publish some results on RC series defects from CBN. So that's another material of interest for us. But I'll be talking about, again, mainly NV-diamond today. Actually, I'll not go in detail, and actually my whole presentation will be short, and we can have discussion about our results. I can try to answer questions after my slides. So I don't have many slides today. And I will actually skip this slides. I'm assuming that the audience here knows how the NV-diamond works. But if there's questions about this at the end, I can go back to the slides and answer. So I'll just skip it. I'm sure most of you know how it works, and we are interested in magnetometry applications. So here in these two slides, I explain it, but I'll just skip it for today. So for us, a strength for us is the antenna design and fabrication for this quantum sensing experiments with solid state defects. We have a publication here, you can check in detail. We were able to fabricate a very efficient RF antennas with over 30 dB loss at desired 2.87 gigahertz frequency for NV diamond, and we demonstrated quantum sensing magnetometry without using an RF amplifier. So they were so efficient, they can work like with 0 dBm output from an RF signal generator. That actually helped us to develop this compact quantum sensors, which I'll talk in the later part of this presentation. And we keep developing these antennas for different applications. As you can see, some new ones with smaller footprint. And for different experiments, we also designed different type of antennas. Here, these are coplanar or microstrip antennas, but we design also different wire antennas or different types of materials as well, like antennas fabricated by lithography, deposition techniques. So that's a strength in our research group. We are good at this, and that's helping us to carry out different experiments. So most of you, I'm sure, are familiar with this paper from Wadsworth. And they did use bulk diamond and NV defects to detect action potentials from a marine worm. A research group in Denmark, I think they also got similar results. So they used NV diamond magnetometry to record these action potentials from these organisms published here. So that's sort of our motivation. Can we detect subcellular action potentials with NV defects in nanodiamond? Bulk is already demonstrated from whole organism, but can you do this at subcellular level? That's our motivation. So we did an initial study on this. We got our nanodiamonds from Adamas, and we checked their ODMR. Not a great data here, but we do get much higher resolution data more recently. We compared with bulk diamonds, and we did a preliminary study for action potential recording from cells. So we are not there yet. I'm giving you, the heads up, but it's a preliminary study. So we deposited different size nanodiamonds in mouse brain cells, as you see here in these confocal images. The sizes were 10, 60, 100, and 140 nanometer, average size nanodiamonds. And as you can see in these panels, especially here, FNG, these are 10 and 60 nanometer nanodiamonds. These are confocal images with commercial microscope. The uptake was better efficiency with 10 and 60 nanometer, and with 100 and 140 nanometer, it was less, the uptake, due to size. As you all know, as most of you may know, let me put it that way, nanodiamonds are also used as non-bleaching fluorescence markers. There are many publications on that. It's also used in quantum thermometry, a lot of publications on that too, but there's no really publication on using nanodiamonds for subcellular action potential recording, which is very challenging, very challenging. So we tried it with external magnetic fields just to test the feasibility. We don't have the sensitivity yet. I'll talk about the sensitivity in the later slides. We don't have the sensitivity, which will require like picotesla level sensitivity for magnetic field detection to be able to see those action potentials from cells, and we don't have that. So we applied external magnetic fields, and just to see if it's possible, even if it's possible to do ODMR when these nanodiamonds are within the cell. So these are our results. The panel B here is our bulk diamond ODMR. Again, this is our type of measurement where we don't see more detail. I'll talk about other types of experiments where we see the vector and magnetic fields more efficiently. But this is for a magnetic field in the Z direction of the regular bulk diamond plate. And you see this clear signals. But when we do the same with nanodiamonds in cells and we apply external magnetic fields, in each case, this is about 500, if I remember correctly, 500 microtesla, or maybe 1 millitesla, looking at the numbers here. You see these broad signals, broad dips, and that's definitely due to orientation, random orientations of nanodiamonds. The orientation of the these are obviously the red arrows are representing the spin orientation. If I'm wrong, I would ask Adamas people to correct me. But in any case, their physical orientation compared to the applied magnetic field is definitely random, causing this broadening of these dips, which makes it harder to detect any action potential. And again, the sensitivity is not there. The orientations are a problem. And we are doing CW, continuous wave ODMR, which is also not the best approach for both like good sensitivity measurements. Although the Denmark group did their experiments with CW and with a lot of software or computational post-processing, but they were able to record action potentials as well using bulk diamonds. So that's our preliminary results from nanodiamonds. It's not action potential recording, but the feasibility. So we can do ODMR and magnetic field detection when the nanodiamonds are within the cells. So our next step is improving the sensitivity, obviously, of this magnetic field sensing down to picotesla. Here's a nice study from this group, from this paper. They were able to actually trap single nanodiamonds and determine their orientation compared to the magnetic field from their data. We are hoping to establish setups. We are actually working on it to be able to do these ODMR experiments with higher resolution, hoping to actually go down to a single nanodiamond level and at the same time improve the sensitivity through establishing other hardware improvements, including like pulse magnetometry and lock-in detection methods, which we are working on right now. So that's for our one set of experiments on action potential recording. The other use of nanodiamonds is we deposit them on glass micropipettes, and you might be familiar with this scanning NV diamond magnetometry tips. Q-Saber is a company offering those microscopes from Europe, and they and other research groups all over the world, they make this kind of bulk diamonds, AFM like tips, and they do scanning magnetometry with this kind of tips. So ours is a cost-effective approach. We deposited the nanodiamonds, as I mentioned, on the tip of this glass micropipette, and we try to do scanning experiments with that. That's the antenna that we use in this experiment. Again, we optimized this design, and it was able to deliver microwaves to the tip of this glass micropipette where the nanodiamonds are. And we tested this probe in this custom sample, which I will show in the next slides. Again, this took us a while to make it work. The antenna design, efficient delivery of microwaves to this tip. is challenging. As you can see here, we did design, fabricate this antenna, tested it. Its efficiency is good, over 20 dB loss. And one interesting thing, we are actually, these results that I showed previously on action potential, and these results, we are in the process of submitting them and getting published. They're not published yet, but you will see once it's published as well. The enhancement also helped. The enhancement due to the structure of the micropipette tip. So it's like obviously like a cylinder shape, and we did electromagnetic simulations, and experimentally we observed that if you place nanodiamonds on this micropipette tip, the PL emission is 3 times compared to depositing them on a flat surface, flat glass surface. So through the electromagnetic simulations, we also tested our hypotheses. We believe that this ring-shaped tip enables resonant PL emission, like those micro rings, and we did calculate the, analytically the enhancement here. It actually works over a long distance. It doesn't only work on a spot, on the tip only. It works in a large range due to the dimensions here, and we see that enhancement. That also helps in, in these experiments. We get good signal from nanodiamonds due to this structure. So we tested this probe in a scanning magnetometer setting. We built this custom sample with fragments of permanent magnets in the middle, as you can see, embedded in a polymer. And we scanned and recorded ODMR signals from different ports. This was a manual scan. We can do motorized, but we didn't establish it yet. It was a manual scan of the surface, different ODMR experiments, and as you can see, the nanodiamond probe was able to record higher magnetic fields where the permanent magnets are. Actually, the signal was very strong, and we didn't need to be very close to the surface. We were at a good distance, and this is another, again, study that we are right now getting ready to publish. So in the next part of the talk, I'll talk about the compact quantum sensors. These are some images from our setups. I'm sure you are familiar with this kind of benchtop setups for NV diamond quantum sensing, magnetometry. We do have cryostats. Some of those defects, as I mentioned, as you may know, require low temperature experiments. So we do also do low temperature experiments. As you all know, the diamond is great because it works at room temperature. We don't need a cryostat. And, a lot of people now do this kind of experiments. Everything is mature. And actually, even, as you may know, benchtop diamond microscopes are becoming commercially available. There are several companies selling them. And actually, more recently, there are even more compact versions coming up in the market. SB Quantum, Canadian company, they don't have the exact size on their website, but they have this, for example, compact quantum sensor based on diamond. They're actually testing it for their use in space. They are in this contest, MagQuest, and they are doing CubeSat testing of this NV diamond compact quantum magnetometer. Again, they don't give much information about its weight, size. They say the size of a milk cartoon, and its sensitivity is not known as well. More recently, there's a company from Europe, Qent, has actually started selling this. You can buy one and test it. It has 2 units, like a main electronics, and I believe it's also battery operated. And it weighs about 600 grams, and they actually are claiming 10 picotesla root hertz sensitivity. This is a new publication, recent publication, couple months old from China. They did also demonstrate this magnetometer, compact quantum magnetometer based on diamond with 390 picotesla root hertz sensitivity. The size is like that, and they use FPGA boards, lock-in detection techniques to achieve this, but they don't include, I guess, the computer. I think this still needs to be attached to a computer to get the results. So there's an ongoing work from different parts of the world to develop compact NV diamond quantum magnetometers. Again, it's a mature technology. It can be done. So in our case, we developed this compact quantum sensor in our lab. It measures about 10 by 10 centimeters. This is the lab prototype built with off-the-shelf components. It's battery operated. We call it CQS, and these are some magnetic field testing results. As you can see, it's very reproducible. It works. It's CW right now, and we also employed machine learning algorithms. We developed machine learning models. We collected over 100,000 vectorial magnetic field detection ODMR scans, and then we trained models, and in certain models it went up to 90% of detecting the vectorial magnetic field components of unknown magnetic fields. And this is still not a great ODMR scan result. We have better ones now, but our ODMR scans, magnetic field scans, vectorial magnetic field scans capture the details of the the vectorial magnetic field in this ODMR scans, so we can use that to develop these models and predict unknown magnetic fields vectorially, and went up to 90% efficiency. So based on that success of CQS1, we started building another one with a second version with custom electronic circuits, and it has much better ergonomic shape. It has a touch screen now, and it also works. We can record ODMR with this device. It's still in the testing phase and development phase, and we are working on this as well. It's also CW ODMR. So another application interest for us is magnetolography. MEG is a state-of-the-art non-invasive brain imaging device. It's being used in clinics. It's not a well-known device like EEG. There are 150 of them, and they are mostly discrete-based superconducting circuits. They require helium cooling. The patient needs to be stable, so it's not great for kids. It's being used pre-operation for epilepsy surgeries, and there are other clinical uses for brain-related, like Alzheimer's, brain tumors detection, and also some psychological issue detection. So again, they are bulky, expensive. The current ones expensive to operate as well. It requires liquid helium. So again, the question is, can we do this with diamond? And the other more recently developed MEG devices are based on OPMs, optically pumped magnetometers. And as you may know, they require heating over 100 Celsius, but Brainbox, British company, started selling them. So the question is, can we make this with NV diamonds? So we built this prototype fiber-based. As you can see, this phantom head, we tested it in our lab. There's a small electromagnet inside this phantom head, and we demonstrate that it can detect, again, microtesla level magnetic fields. A more recent version here, as you see on this right type, this prototype. In this one, I mean, the first prototype, it's fiber-based, the laser is being coupled, and the emission is collected through the fiber, but here, the excitation source and emission collection is all happening in this small probe here. RF antenna diamond is all here, and we are working on this prototype actually now to see if we can improve its efficiency, which is another challenging project because MEG sensitivity requires about like 50 femtotesla sensitivity, and as you all know, there are publications claiming that they are getting femtotesla level sensitivity from a couple groups, but it's also very challenging. But it's something that we are working on as well. We are trying, as I mentioned, we are using CW approach, and we are trying to implement pulse ODMR methods, especially Ramsey, to improve the sensitivity of our devices. And we are actually trying to do this in a different way compared to other people, because most people do this with benchtop setups. Because we have interest in compact quantum sensors, we are trying to develop hardware so that we can do this also in our compact quantum sensors. Another research project is, can we develop this compact quantum sensors even at smaller scale, at micron scale? So we are currently running electromagnetic simulations, designing structures, micron scale waveguides, and other photonic structures to see if we can make this in a photonic quantum circuit or photonic integrated circuit level, so we can get micron scale devices. Here's a simple waveguide structure with Bragg gratings. As you can see here in this transmittance data, if you give green and red from one side, if you build this from diamond, it can actually block the laser excitation on the other side, and hopefully red emission coming from the diamond. This is one structure, initial structure. More recently, we are using this inverse design approach, inverse design of photonic structures. If you are not familiar, in this case, and these electromagnetic simulations, you tell the computer your desired output, and the computer actually designs the structure for you. That's why it's called inverse design. It uses machine learning algorithms, and it actually gives you these non-intuitive designs, but they work. So there are demonstrations of different devices. So we are trying to implement this to NV diamonds. As you can see, this structure that we recently obtained from simulations if you give red and green emission, that's green laser excitation, and the red emission from diamond from this left side, this structure can efficiently filter out the green laser. As you see this transmission curve, the channel 1 transmits the green laser. It diverts the green laser to one channel, and the diamond emission to the other channel is shown here. And we are optimizing the structure. We'll be fabricating and testing it in our lab, and we are hoping to again reduce the size of our devices even further, and maybe even make arrays of any diamond quantum sensors, especially for magnetic field sensing applications. So as I mentioned, it will be a short talk. Here's my summary. Again, we are good at designing and fabricating RF antennas for different solid-state defects, not only diamond, but also other defects in other materials as well. We did obtain some preliminary results on the feasibility of using nanodiamonds for subcellular action potential detection. We are working on it. We developed a low-cost nanodiamond probe, as I mentioned, and we're developing this Nanodiamond-based compact quantum sensors, and we're using machine learning to improve its efficiency. This is my research group at Morgan State, postdoctoral researcher and graduate students, research technician, undergrads, my collaborators at Morgan and elsewhere. Funding comes from these agencies. And thank you for your attention.
Birol, thank you very much. It's very interesting and it's so exciting to see how you are focused on practical devices, on portability, on real life problems to be addressed within these centers.
Thank you.
So we are open for a discussion. Just unmute yourself and ask your question.
Hi, can I have
please.
This is Tony from Adamas. May I have a question? What kind of software do you use for magnetic simulations? Is it like HFSS or console?
We use HFSS mainly
Okay.
For the RF antennas, and we also use a CSD Microwave Studio, but mainly
Okay.
HFSS.
Thank you.
And I guess I'll follow up, just a quick question. So I noticed that when your microwave antenna are very well tuned, you have a very sharp bandwidth. So maybe like on slide 5, for example, or even there. Yeah, this is great. But so as these peaks shift, you're going to see a change in the microwave intensity. And then wouldn't that cause some difficulties, or how do you address that?
That's a good question. I mean, again, these are just some of the examples. As you can see on this right side, it has broader dip, and we have actually other versions where it's even broader. They work in a broad range of frequencies, so we can engineer them to work efficiently over a 1 gigahertz range.
Mm-hmm.
Depending on the application, we choose different design.
Cool. All right, thanks.
You're welcome.
Birol, can you please elaborate a little bit more on diamonds that you use in your portable devices that you presented at your portable magnetometers that you presented at the end of your talk? And what would be your requirements? What would be your ideal diamond sample for your application?
That's a good question. So we are using element 6, the MBB14, as like I showed some pictures here, the pink diamond, we call it the pink diamond, in this experiments. And the main reason is, it has good emission, good counts, and to be able to squeeze these things into small compact forms, you have to sacrifice from other elements like the laser power and collection efficiency. So having a bright emission helps. So that's why so far we focused on that. But as I mentioned, like we are open to other types of diamonds, and we are testing your diamonds right now as a alternative. We'll see how that works. And mainly, element 6 diamonds are getting more expensive, including the tariffs, especially after tariffs. So we are looking at alternative resources as well, but right now it's all element 6.
And what's about, say, lateral dimensions and thickness of diamond for this type of application? Again, the larger substrate size, higher non-uniformity becomes in terms of magnetic field gradient at these distances of few millimeters. Is it a concern as well for microwaves non-uniformity across this size diamond sample?
So we are using the standard size as received size, which is about 3 by 3 millimeter plate, I believe 0.5 millimeter thickness. And you know, they have a change. We know that the center of this crystal behaves slightly different than its edges, and we actually documented and shared it with you. So in these devices, so far we haven't, you know, tried to check the, you know, which part of the diamond will work better or what's the difference in terms of device performance. We did those tests on benchtop setups, but not in the devices. And we are actually hoping to see, like, that's the test that we are working on right now, to see if we can use smaller size, maybe up to like a millimeter, the millimeter size plates. I didn't mention, but this device here with the, especially the fiber one, we actually use one of your micro diamonds, which work great. It has really nice emission, but on this prototype, the new prototype, we are using still element 6 plate on this one. It's a bulk plate. So it's really, you know, it's a trade-off. We have to have, of course, high quality diamond uniform properties. Having it as a plate helps in terms of determining the vectorial components, how they interact, its orientation in the magnetic field. It's easier if it's a plate. But, you know, we also need to do it in a cost-efficient way. So they're trying to balance that.
Can you please also list desired quantum characteristics from diamond that you use for sensing? Say ODMR contrast, at which range would be preferred, or say width of ODMR dips and so on. Is it some desired numbers in your head to share so that developers can kind of target those numbers?
Sure. That's a good question. So, because we do CW ODMR so far, you know, we don't pay attention to like T1, T2 times, coherence times. We don't really pay attention to that. For us, the first and most important so far criteria is its brightness of emission, so that we can actually make this compact devices work. In terms of contrast, you know, it's we don't. I mean, we are getting. I should say we have some control over it, but the contrast can be as low as like 0.5%. Okay, as long as you have a clean background, like if you can clean other noise effects, 0.5% contrast can work if you have a clean background. And we did have great spectra, ODMR spectra, vectorial magnetic field detection with as low as 0.5% contrast, and we were still able to detect these vectorial components using these machine learning models. But you know, a good efficiency in these devices is about 2-3%, and on our benchtop settings, you know, we get like 7 to 10% contrast. But you know, all these setups, they have their different ODMR mechanisms, different hardware is used. So especially in these devices, smaller devices, the hardware that we developed helps us to get this detailed spectra. I mean, like this one, it's not very. You may think that it's It's not a great one. We do have higher resolution spectra, ODMR scans with more like better details, I should say. And in this one, as you can see, it's actually about like 1%, but still we can get good information about the vector and magnetic field. So it depends. It's relative. Like if it's clean, the contrast can be small. If not, we need, of course, a little bit higher contrast.
Okay, thank you.
Welcome.
Hi, sir. Like, while moving to the portable magnetometer, what is the major challenge you faced? Like, we are moving into more compacting, and also even when moving to the lenses, like collection of the maximum fluorescence, and like, is it any limit? Like, you can say this much is sufficient for going to a better magnetometer, and when we move more and more compact, like the efficiency should obviously it might decrease, right? And for this optical stimulations and all, like how you figured it, like optically, like, or designing the lens and these things, what are the major challenges faced?
You know, you're packing a lot of electronics into a small volume. So heat dissipation is a major challenge. So something we are working on. It's getting better. That's major challenge. And the sensitivities are comparable actually to our desktop settings because so far we have been doing CW, and actually the hardware that we employed in the developing in this smaller compact versions, interestingly, they are providing better resolution compared to our desktop hardware. So we are even switching our desktop hardware to the similar hardware that we are using for compact sensors, interestingly. And again, the sensitivity, we are addressing it at the same time developing pulsed approach, pulse ODMR approach, which actually requires a lot more electronics development, which we are working on. It's a challenge, technical challenge, making these things work in a smaller volume with smaller footprint devices. And in terms of optics, we are not really focused on improving the alignment in the optical module, what we call optical module in this device. We were not paying too much attention. We were just using this bright diamonds, but that's something that we started paying attention. We are putting in more controls in the optical module so we can improve the alignment and get better counts with diamonds, which has less brightness, less bright emissions. So there are a lot of technical challenges, of course, we are addressing at the same time.
So rather than moving, like focusing on much optical stimulation, you are working on taking a better diamond, which can give maximum. Is it?
Yes, yes, that's our current approach. So far we have
Okay.
been doing that instead of running bunch of optical simulations. These are ray optics, of course. These are different type of simulations. Instead of doing that, we were using bright diamonds, but right now we are including more alignment controls to improve the efficiency, so we can use diamonds with less brightness.
And also, like from your experience, like how you comment on it, like we are doing them simulations and again coming to the real experiment, like should we actually is it possible to compare it, or will it give some proper results, like suppose Emacs or anything, some
I think
simulation?
it's useful if you have that capability. running Zmax simulations, choosing the correct parts, optical parts accordingly, or build your own parts. I think that's definitely useful. But
Okay.
in our approach, we just tried and it worked. Especially with this device, we always say we got lucky, and now we are improving its efficiency.
Okay. So, and what is the range of magnetic field currently you're measuring, like in picotesla or like
Oh, no,
in the
this
current?
is yeah. Right now it's microtesla sensitivity, and
Okay.
currently we are trying to see if we can push it down to nanotesla, and this is all
Okay.
CW.
Okay.
And to
Okay.
achieve picotesla, again, we are developing those additional capabilities, hardware capabilities, so we can also achieve picotesla sensitivity.
Okay. Thank you, sir.
Thank you.
Yeah, thanks for your talk. I have a few questions. Can you elaborate more on what is used as components? You briefly said you use commercial off-the-shelf components inside this portable device. So maybe you can elaborate what type of laser did you use? Do you use additional optics? Do you use a standard photodiode? What are the color filters that you used for that? And also the question is, how much laser power do you need for these sort of ODMR spectra?
Okay, so this one is a patented technology now. It's IP protected. I can't tell much about the details, but I can say we do use a diode laser, some good power of diode laser. Again, heat dissipation becomes an issue. The other parts are standard optics filters that you will use in a benchtop setup, just smaller versions. Yes, photodiodes, and again, our biggest strength is the efficient antenna that helps to use lower powers in these devices. I think that's as much as I can say.
Okay, thanks. And do you observe any hyperfine splitting on these setups already?
Yes, I'm not showing the again most detailed results, but we do, and we do get very high resolution spectra with these devices.
Thank you very much.
Thank you.
And Birol, with this device, how you do measurement? Do you, I mean, say if there, it is kind of a macroscopic magnetic field, right? So it is not, say, critical to have some point where you bring your device right on a micro scale. So at the moment it is, say, there is some diamond placed in some, like in that Q-Sense company that you showed as a company, they have a diamond picture symbol where you kind of know that your diamond is located, and then if you want some, say, millimeter scale magnetic field, then you bring your sample to that point on your device, just kind of.
Yeah, so yes, it's a good question. The diamond is within the box, and it's not designed to bring close to a surface where you expect very small magnetic fields. So it's really for the small magnetic fields in the environment. So we for testing it, we put this in a large Helmholtz coil, apply vector magnetic fields, collect that data. So it's not really localized magnetic field. But the other version, of course, for brain imaging, the diamond is on the tip of this devices, of this probes. And in this case, it has to be because this will be sitting on the scalp, like this kind of setting, OPM setting here. And it has to be as close as possible to the source of the magnetic field. And we also are planning to implement this in our handheld magnetometers, compact magnetometers, where the actual diamond will stick out from the box, from the tip, and then we'll be able to touch to surfaces to even detect much smaller magnetic fields, localized magnetic fields as well. So that's part of the plan as well. Yeah, we are developing it mainly for brain imaging, but it will get there too.
Okay, thank you.
Thank you.
Sir, could you please slightly,
Yes.
yeah, okay, great. You can continue. It's okay, you can continue.
Please ask your question. Yeah.
Thank you. Sir, could you please explain on the design of this microwave antenna? And you mentioned the micropipette. We are placing the nanodiamond on the tip of the micropipette.
Yes.
Like, could you please, like, how it helps actually the design of that?
So, there's like the micropipettes. I guess you can purchase them, but we have a puller, micropipette puller. It's a standard equipment, and most neuroscience labs who are doing like electrophysiology, they take this cylindrical glass tube and you pull it, and then it forms this taper. You can go down to submicron tip diameter, and then we actually simply dip it in the nanodiamond solution, like we do it usually multiple times, and each time we dry, and to increase the concentration, we dip it multiple times, and then we built this spatial antenna for this purpose, so that it efficiently delivers the microwave to the nanodiamonds on the tip. And as you can see, this is a benchtop setup, of course. Laser is focused with an objective, and we collect the emission with the same objective, its reflection mode. And this probe scans the surface, and we collect ODMR scans at different points, and that's how we form that image. Does that help? Do you need more information?
Like this pipette, this micropipette end will be going into this antenna, right?
Yes.
That curly structure.
You can see in this top right corner image, it's a very thin tip, but we keep the antenna part a little bit above the surface, so that when you're doing the scan, it doesn't touch the surface.
Okay, but so it's little far. But from in the other slide, the next slide, I found it's kind of placed inside of anything. I don't know, like.
Yes, it
the
is.
left.
This is like a top-down image. I need to check with the student if they did push this a little bit down. It's a 3D simulation, so it might be a little bit down. This is the top-down view.
Okay. Thank you.
You're welcome.
Do we have more questions? I think it was very comprehensive answers and great discussion of the Birol's work. So at the moment, I want to thank Birol very much for your very interesting presentation. I would like to thank audience for your questions and interest, and have a great day or evening or morning, whatever part of the world you are. Okay, thank you everybody. Bye. Till September.
Okay, bye.
Thank you. Bye.
Birol, thank you so much. It was great.